All right. Got your test back. Very pleased. And I hope that you are too. And so those are yours to treasure forever. Use them for studying for the final. That might be good because it's going to come back to haunt you. All right. Haunt, but in like a nice way. Maybe. Oh yeah, should I bring that up again? So if this test was not what you were hoping, as long as the final exam is better, then I'll shift one of the test weights to the final exam. Okay. Obviously, I can't do that until you've written the final exam, but there is hope. Just improve, and that's all I ask. It's a simple ask, really. Learn the material at some point before the final. So, and of course, if you were sick, I was terribly sick at the end of last week. Well, I was kind of pseudo sick all week, but terribly sick at the end of last week. Just well enough for Monday, right? That's how it goes. And so now I'm all behind again. Just terrible. All right, let's see here. Little bit of review. I hadn't posted the finished notes for chapter 5, so I did update that. So if you don't have the hypothesis testing notes, then you'll need to re-download them from Moodle. But I didn't change the name or anything, which was at the door. Yeah. I need like a buzzer to buzz people in or something. Or they could just leave the door unlocked. That would be nice. So we introduced confidence intervals last week, I guess. And confidence intervals were our first foray into inference, right? Where we're taking sample information to learn about the population. And so we talked about a confidence intervals. And you know what? I'm gonna treat myself with a whole fresh page here. Let's see. So I don't have to squeeze it onto here. There. I need some lines. Okay. Confidence intervals. In general, we take some point estimate, and what we started talking about was, okay, what if I have one sample and I have some proportion, so some sample proportion, then that's my point estimate. Okay. And then what we said was, okay, we can use that point estimate and we can build out a little, a buffer is how I think of it, right? And so my kind of intuitive example is how far is it from here to my place? And then, so I have my best guess, let's say 4 kilometers, 5 kilometers, I don't know. 4 plus or minus 1 kilometer, quite a big interval, right? I'm not very sure in my estimate. My point estimate of 4 wasn't very good. So then I put huge buffers on, right? Or we're going to call it, and I don't think I called it a critical value last day. So that's new. So I want to talk about that. But times the standard error, and I'm going to need more room here, times the standard error of the point estimate. Ugh. Pointest. Of the point estimate. There. The critical value, we said, okay, if I want to make a 95% confidence interval, we kind of dug a little bit deeper and we said, okay, that's plus or minus 2 standard errors, right? And then we said, well, we can get a little bit more specific than that. And what we're going to do is we're just going to replace this with a Z star. Now, Z star is what dictates the confidence level. Z star gives the confidence level. Oh no, I was going to bring the t-tables today. To punish myself, I'm going to write in red. Emily Stern. Emily, bring t-tables on Wednesday. T-tables on Wednesday. All right, close enough. Okay. Why did we want the t-tables? Had that sneaky way of finding this Z star because my slowpoke iPad here. This is the t-table. We're ignoring everything except for the top row and essentially the bottom row for now. And the top row gives us the confidence level. So I feed it whatever confidence level I want. Let's say 95%. Oops. Let's say 95% confidence level. That's going to be our default. And then down here at the bottom is a Z star. Okay. So it just tells us what to use. You can solve those using the Z table, right? You force 95% to be in the middle, which means you have 5% split evenly amongst the tails. You know how to solve those, but it's very tedious, right? And so I don't want to do that. And so here, Z star for a 95% confidence interval is 1.96. Gives the confidence level, use the t-table to find it. Z star is 1.960 for a 95% CI, confidential informant, or confidence interval. Door. No. Game over. I just wish that they would leave the door unlocked. But everyone would be so confused. Everyone would just be waiting because now you're trained. Oh, sorry.
No, that's fine.
You can move those if you want.
Don't worry.
A wealth of tests. Okay, so we know how to find Z star the long way. That's okay, but now we have a shortcut. That's great. And so what else? We also introduced, okay, the point estimate, the only point estimate that we've introduced so far is the sample proportion, right? And as we make our way through the next couple of sections, we're going to change the point estimate, right? We're going to have a different scenario. So the point estimate is going to change, which means that I also have to tell you what the standard error of the point estimate is. And I use a little SE subscript P hat to indicate that that's the standard error of P hat, okay? And so for each scenario, those are the two things that I need to tell you, right, what they are. And then you'll be able to build a confidence interval. Just kind of go in blind, pick and plug and chug, and then you're there. right? So that's confusing in the beginning, but later it's the perfect recipe, right? Because it'll always work. We also said that the standard error of p hat is going to be p hat q hat over n, and then all square rooted, where q hat is 1 minus p hat. Q is just the opposite of p. Right? So what does that mean? It means that usually in order to find p hat is the number of successes over n, right? And so notice that p hat is the x over n, which is the number of successes divided by n. If you take a step back, there are only two things that we need to have everything, right? We need the number of successes and we need n. Or the alternative would be if I tell you that 0.67 out of 400, right, then you can work this back and find the number of successes if you need it, right? But all you need is x and n, right? Or p hat and n is even better, because then you have p hat and you have p hat, you have 1 minus p hat, feeling good, and then you have n, right? And so in terms of how much information you need, there's very, very little, right? And so I'll say, therefore, a question only needs to give you p hat or x, the number of successes. And I'm just going to use x as the number of successes. Okay, so just kind of keep that straight. And n, in order for you to have all the information that you need, in order to have everything you need. That doesn't really make sense, but moving on. Yeah. So that's good, right? It's a matter of combining these things. And let's see here. Better be on your formula sheet. One sample proportion . So slow. So I give you the sampling distribution of p hat. You can kind of ignore that. That's just a fact, and that's just me being a little bit obsessive, I guess. You can ignore this. What we need is this, right? And so a confidence interval for p, because remember, we know exactly what p hat is. We saw it. And so our confidence interval is not trying to figure out what p hat is, because we're building our interval around it, right? What are we trying to do? We're trying to throw that net out and trying to catch the population proportion, right? And so the confidence interval is for p, and I write this on the formula sheet as a way to guide you in the right direction. The right direction for what? For your interpretation, right? And so this is very important, okay? Which leads me to the next slide, just beautifully, I might add. End of review. sort of. Okay. So interpreting confidence intervals, one of the main things about interpreting the confidence interval is that it's always about the population. I'm 95% confident that this interval from here to here captures, right? Because I want to kind of invoke that imagery of trying to capture this unknown thing, the population proportion. Okay. Notice that it's not specifying here the population what? And that's because we're going to talk about the population proportion, the difference in population proportions if I have two samples. Then we're going to move on to means, the difference in means, right? And so there's going to be a lot of different populations that we talk about, but the framework is the same. So that's nice. These are not probability statements, right? We're just 95% confident, right? And so a little bit finicky, right? You never want to say the probability of I can't even get there. I've read it so many times. No, that's not it. The probability of something, that's not what you want to say. Good thing I didn't say anything. Okay, so it's only about population parameters, not individual observations. So it has to be about population proportions and not just a single success failure, for example. And then of course, we have to check conditions because it only works if our sample is unbiased. So if it's randomly sampled, right, and things like that. And so we'll talk about that today. But in general, interpretation, I want, until you're ready to take your training wheels off, which may be never, and that's totally fine by me. Whoa, sounds grave. What's going on here? Until you're ready to take your training wheels off, I want you to use this exact sentence structure, okay? And so it's a matter of memorizing it until it clicks. One day it will, I promise. And then you'll say, well, of course, that's how it is. Okay. So instead of making you fumble through kind of a bunch of wrong interpretations, I just want to give you the right one and only that one. I usually say something like, we are blank %, right? Whether you made a 95, 90, 98% confidence interval, right? Something. We're blank % confident. The interval from blank to blank. Now, I do want to make a note here that this has to be the lower to the upper bound. Okay. You've got that plus minus, so you want to do the minus part and then the plus part. Okay. Why? The interval from 3 to 1 doesn't exist. The interval from 1 to 3 exists, right? So just be careful with that. That's my mathy side showing. It doesn't exist. Okay, we're 95% confident that the interval from 1 to 3, for example, captures the population, and here I'll just say parameter, but for now, okay, this parameter, we just steal it. You reword the question as an answer. Construct a 90% confidence interval for the proportion of adults who live at home. I don't know. That's one of the examples we use later, right? And so you just reword it. I'm 90% confident that the interval from here to here captures the population proportion of adults living at home, right? And so here, reword the question as an answer. But the most important part is that you have the population in there. Okay. Sometimes I replace that with true if it sounds better. Whoops. The true proportion, for example, right? Or true is kind of a go-to move, right? And so, but if you say population always, then that emphasizes to me that you know that you're trying to capture the population, and that's a good thing. Okay. Whew. And that's just confidence intervals. Okay. Always, 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 when I make you do a confidence interval, part of those marks will be the interpretation, right? I tried to nudge you in that direction, right? Interpret the interval. So what, you can do math, great. But interpreting the interval, that's going to be the most important part for us, right? So that's going to be half the marks. Half the marks? Yeah, well, I mean, you did pretty basic math, right? P hat plus minus 2 times something. And so it's not, not crazy. What does 95% confident mean? Okay, so let's pretend or simulate that we took a bunch of different samples, right? In our scenario, and whenever we're doing any sort of statistics, we only take one sample and we use that information, okay? But the reason that we're only 95% confident, and I'm going to change this population proportion because we haven't introduced the mean, but of course it works the same for the mean. Yeah. And so what happens is, okay, so if I have a population proportion, P here, that's this line, okay? So I know the population proportion. And if I do say so myself, I made a beautiful lab for this week that I just finished because I had some coding problems that I had to ask Steve for help with, where I make you experience the central limit theorem. I give you the population and then we sample from it. And then we do it 100 times. Well, I do it for you and I give it to you, make you do it once, show you how it's done, show you how it's done. And then what do we see? Then each of these, right, if we know what the population proportion is, then our sample proportions, we expect to be hovering around. Now I'm way far away from my population proportion, right? We expect to be hovering around the population proportion, not necessarily exactly the same. There's some variability there. And so each of these are little p hats. And then I've built my interval, right, around that. All of these are capturing the population proportion. We don't see that, but this is just how it is. It's just how it is. What if our sample was this guy? There's no way that we could know that, right? We sampled properly, we did random sampling, we checked all the conditions, which we'll talk more about today, and we did our best. And still, what if this is it? What if this is our p hat, right? So this could be our p hat. And that's why we're only 95% confident, because 95% of the samples are capturing the population proportion, but 5% of them are not, right? And so that's why, right? We assume that we are one of these good ones, right? But there's a chance, there's a 5% chance that we're not, right? That we're this guy. Yeah? But this also emphasizes that you're trying to capture the population proportion, even though we don't know what it is, right? And we don't need to know what it is. All right. Time flies when you're having fun, huh? Especially for me. I don't know why it says remember when. I don't remember when we introduced this gender discrimination experiment. So that's, I don't remember. Have we? Did we? Maybe it's like, remember when this was a thing? Maybe. Anyways, just don't remember when, just notice or something. So we're introducing this gender discrimination experiment where we looked at obviously gender, males and females, and whether they were promoted or not promoted. Okay? Depending on what you define as a success, right, that'll determine how your p-hats are calculated, right? And so here, if we're interested in whether they got a promotion or not, right, then I would call that a success, right? You could flip the script and say not promoted, but what's going to happen? That's just kind of the complement, essentially, right? And so you're not really talking about anything different. It's just the interpretation is going to change. Okay. So what we can do is we can find the sample proportion of males who were promoted, right? 21 out of 24. Careful that you don't use the 48 in this case, right? Because that would be the out of the total sample, and you just want out of the males, how many were promoted, and then out of the females, how many were promoted. Notice number of successes out of your sample size. Hey, that's all we need. All the rest is gravy. So here, this is the number of successes. And here are the totals. All right. Now we're not going to be ready to do this example yet, because why? Because I have two samples, right? I want to compare sample proportion of the females to the sample proportion of the males, which you're going to have to wait until maybe just Wednesday to do that. So it's not far away, I promise. Okay, fine, maybe Monday. We can use it to introduce some of these ideas behind hypothesis testing, right, which is what we're doing. I didn't write it down. This is section 5.3. Yeah, 5.3. So hypothesis testing, it's kind of a big one. And what you're going to find is that there are a lot of rules that we introduce here, but don't worry, those same rules are going to apply throughout the rest of the course, save the last week where we do some fun stuff. No, this is the fun stuff. I take that all back. So hypothesis testing, if you think back to, I don't know, for some reason I think about Science 9, we had to come up with some hypothesis, a scientific hypothesis, right? If I heat up ice, it'll melt, that kind of thing, right? And so we're going to do the same thing, but a little bit more, well, a lot more rigorous, I guess, not just ideas, okay? And so what do we want to know? We want to know if these two things are independent of each other, right? Is 0.88, is it significantly different from 0.58? Your gut reaction might say, yeah, right? But what if I introduce the spreads on these things, right? What if the spreads are huge? Then all of a sudden a difference of 0.3, I think, isn't that big, right? So it all comes down to the spread, right? And so what we're going to do for our hypothesis testing is we're going to start with this null hypothesis. So the null hypothesis is going to be that everything is the same. These two things are the same. We assume everything's the same, nothing's going on until we have proof otherwise. We usually are trying to prove that we have proof otherwise, right? Depends on the scenario, right? And so then we introduce this alternative hypothesis where something is going on, right? And that's where we highlight, okay, yeah, these two things are not independent, and here's why. We didn't do this, so just don't look at that. I don't know where they came from, but they did a simulation at some point, didn't tell us about it, and now we're supposed to remember. But what we're gonna find is that, okay, if we do a simulation, maybe I shouldn't have scratched it all out like that so harshly. Fine. We didn't do this simulation. Okay. So what we can do is we can assume that these two proportions are the same. Okay. And then what we can do is we can find, okay, well, how many of these differences are larger than 0.3, right? We saw a difference of proportions of 0.3. So here, the difference in proportions is 0.3. So then we can simulate these things, and I know that's all black box stuff. We run a simulation. Calculate the difference in the promotions, right? Assuming that they're the same, they're centered on 0, fair enough. And what we're going to find here at 0.3 is that the probability of seeing a difference of 0.3 or greater is very, very small, right? So here, the proportion of differences greater than 0.3 is very small. Now we use that as evidence against the null hypothesis. Okay. So here, we use this as evidence against the null hypothesis. Okay. Again, I've got so much beef with these slides, but they are saving me a ton of work. So it's easy to critique them, right, when you haven't made them. It's not a recap. Here's an introduction to the hypothesis testing framework. Okay, so hypothesis testing, we're going to follow 4 steps. I like to break it up into 4 steps, although the 4th step has 3 steps. I know, rude. So depending on what textbook you're reading, they like to break it up into different steps. Okay. But for us, hypothesis testing framework has 4 steps. Step 1 is to figure out what your null and your alternative hypotheses are. Now that's going to be a little bit easier with an example, okay? But remember that the null hypothesis represents the status quo, which in our case means it's always going to have an equal sign. Okay. We'll always have an equal sign. That's good to start with. Now, what are we going to be hypothesizing about? Maybe I'll just I'm going to add a page here. Step 1 is to state the hypotheses. I'll capitalize for now. These are statements, okay? And we use an H subscript 0 to indicate that this is my null hypothesis, which you can remember as no change, which means that there's an equal sign. Now, where does this equal sign go? First, notice that this is a statement, right? And so we've got the colon here. I don't want to see any equal signs because it's not going to be equal to anything. It's just a statement. Okay. Lots of little nitty gritty things that I'm going to be particular about. In general, it's going to be about the parameter, right? My hypothesis is not about the sample. I can see the sample. I can find everything I want from the sample. So that's not interesting. But we use the sample to learn about the population. And so my hypothesis has to be about the parameter. The parameter is equal to some hypothesized value. Now, for us, for one sample proportion, your null hypothesis is going to look like this. P, which is your parameter, right? Your population proportion is equal to some P naught. Didn't look very nice, right? Some hypothesized proportion. Okay. Where P naught is a number, specifically a proportion, but I feel like saying proportion so many times might get confusing. Okay. Has to be a number between 0 and 1. How about that? That is a proportion. On your formula sheet, this is on your where is it? Formula sheet, promise. I'll grab the whole kit and caboodle here. Okay. So on your formula sheet, right? I give you the null hypothesis because if P is equal to P naught, so if I want to show that the proportion is different from 0.5, let's say, right? Then, well, if I want to show that the proportion is different from 0.5, then I first have to assume that the proportion is 0.5 until I have proof otherwise. Okay. So your alternative hypothesis from here, HA, can be P is not equal to P naught. This is what we call a two-sided test. I don't care which direction it's going in. I just want to know, are they not the same? So this is called a two-sided test. because I know, buckle up. I want the area in both tails. If it's centered on P, then if P hat is down here, then I replicate it up top. It could have just as well happened on the upper end. And that's why we call it a two-sided test, because I've moved out far enough for this P hat to be considered different from P. Yeah. Blame you if it's not clicking yet. And is this when I confess that for my first stats class, it wasn't until I was studying for the final exam that I was like, oh, okay. I was just kind of like trained to do it. I could pull it off, but it wasn't until I was studying for the final, which is honestly quite a ways away from now. I was pulling it off. Oh, I see. What are the other options? Or I could have P is less than P naught. Or I could have P is greater than P naught. Oh, and this should be a P naught there. Those are what we call one-sided tests because I'm only concerned with one of the tails. Okay? And so here, this is a one-sided test. And this is also a one-sided test. Now, visually, what we're going to be going for here is P naught. If P hat is less than P naught, then the area that I'm going to want is the lower tail. If P hat is greater than P naught, then I'm going to want the upper tail. As a default, if you're ever unsure of what sign to use here, right? Notice that we already used the equal sign here. So that's off the table. And so we only have these three options. If you're ever unsure, then this is your default. Okay. So if you're ever unsure, or if you just want to play it safe, that's totally fine. Then just use a not equal to. Okay. And we'll talk more about why that's playing it safe later on. Okay. Ooh, all right. That was step one. Oh my gosh. Step two. And honestly, step one is the hardest. Trying to figure out what it is you want to prove, right, is the hardest part. Step two is, I call it do the test. Do the do. It just sounds cooler. But what I should be saying is calculate the test statistic. Ugh. Or calculate the test statistic. We already kind of hinted at wanting some area in the tails. If I have a normal distribution, well, we already know how to find areas under the curve, right? Using the Z distribution, which means that I need a Z, which is my test statistic for a one sample proportion. So, and it's also on your formula sheet. Oh, I guess that works. Whatever. So the test statistic here is this Z. One thing to notice is that you would expect Z to be the point estimate minus the hypothesized proportion. I think we can all kind of, if we think about it long enough, I'm not going to let you yet, but if you think about it long enough, if I want to figure out how far is my point estimate from my hypothesized proportion, then okay, I can find that using the standard error of my point estimate. But notice that this looks different than the p hat q hat over n. Okay, and that's because I have some hypothesized proportion. So notice that the standard error now uses p naught instead of p hat. Okay. The reason for that is we do all our testing assuming that the null hypothesis is true. Okay. And the reason we do all our testing, or hypothesis testing, assuming H naught is true, which means if H naught is true, then we're saying that the population proportion is P naught. We were only using P hat because it was our best guess, right? But now we're saying, hey, I'm going to assume that this is true. And so now I can have this more appropriate standard error. We're only going to have this for hypothesis testing. For confidence intervals, we don't have it anymore, right? Then we're back to p hats. But it's on your formula sheet. Just be really careful when you're reading those. Is it p hat or is it p naught, right? But then, once you have a Z, what can you do? You can use a Z table to find the area under the curve. Now, the area that you want is going to depend on your alternative hypothesis, right? If you have a not equal to in your alternative, then you want to find the area in one tail and then pretend that it happened in the other tail by multiplying by 2, right? That's tricky, but that's okay. Or if you have a one-sided test, then you just need to find the area in one of the tails, right? And the appropriate tail. Okay. What are we doing there? Well, we're doing step 3. Really kind of going rogue from the slides here. Step 3, find the p-value. Find the p-value. What is the p-value? P-value is usually something kind of mythical. There's a lot of p's floating around, right? And this one is unique. Okay? And the p-value, see if I can remember exact definition. It's the probability of seeing something as extreme or more extreme than what you saw, assuming that the null hypothesis is true. Okay? It's the probability of, and I'm being generic here because the p-value applies to all the different scenarios that we're going to see. And so seeing something as extreme or more extreme than what we saw in our sample assuming the null hypothesis is true. Wait, true. There. Ah. Doesn't really sound good, does it? But if we reword it, in the case of one sample proportions, or one sample proportion, the p-value is the probability of seeing p hat, the probability of seeing p hat, or maybe I'll say seeing a p hat as extreme or more extreme than our p hat, assuming H naught, which says P is equal to P naught, is true. The probability is the area under the curve. Area under the curve. Okay, so it's the area under the curve of seeing a P hat as extreme or more extreme. Now, that's just generic talk for into the tails. Okay, if you're above the hypothesized proportion, then it's in the top tail. If you're below the hypothesized proportion, then you're in the bottom tail, right? And so as extreme or more extreme is just referring to the area in the tails, potentially tails, depending on your alternative hypothesis. It's a web. I was going to say a web of lies, but no. Lies, damn lies, and statistics. You guys heard that? Anyways, I can't remember who said it. Is it Churchill? Someone famous. Anyways. And this depends on HA. So, okay, what does it look like if the alternative hypothesis is that P is not equal to P naught? Then now might make a little bit more sense when we see this curve. I'll just redraw them. No harm in that. Okay. The tricky part about the not equal to is now I want the area in both the tails, right? But I'm only going to have a p hat on one of the ends, right? I'm only going to have one sample proportion. So let's say, just to illustrate, that p naught is 0.5, right? Which is a pretty standard, right? Is there more than half? Is there less than half? Is it different from half, right? And let's say, for example, that p hat is 0.7. What you would do is you would take this 0.7, which is above 0.5, and you would find this area. Okay. As extreme or more extreme. Okay. But then what we do is, even though this 0.7 only happened on one of the tails, what we're allowing for here, if we're just saying it's not equal to this, then we allow it to go into the tail on the other side as well. Yeah. So here, our p hat will only be on or in one tail, let's say. In one tail. Yeah. But for a two-sided test, and this is a two-sided test, sometimes two-tailed test, but then I get tongue-tied. So I say two-sided test. So our p hat will only be in one tail, but for a two-sided test, we multiply the area in that one tail by 2 to replicate it in the other tail. But for a two-sided test, we multiply the area in the tail by 2 to replicate it in the other tail. It's just a little extra step for a two-sided test. You have a one-sided test, which is kind of a little bit more rare, I guess. But if your alternative is that p is less than p naught, can you use 0.7 to prove that it's less than 0.5? No, right? Because how? Right? 0.7 is greater than 0.5, so there's no way that I could use it to prove that it's less than 0.5, right? In fact, it's evidence against that. Okay, and so you have to be really careful with what you're trying to prove. So p naught here at the center, and if I'm trying to prove that p is less than p naught, well, then I better have some p hat that's less than p naught. I want the probability of seeing something as extreme or more extreme, which is always into the tail, which means that this here is the p-value, or the one-sided p-value. I didn't write two-sided p-value before. Fix that. One-sided p-value, and then the two-sided p-value is 2 times the one-sided p-value. Sneak that in. I will have opportunity to bring that up again, so that's why I'm being a little sly about it. Okay. All right. Now what? Okay. I guess we should finish if HA, the other alternative, is greater than P naught. Well, then first of all, I better hope that my sample proportion is actually greater than P naught. Otherwise, I'm hooped. But P hat then will be on the upper end, which means as extreme or more extreme is this area in the tail, one-sided p-value. So much theory. Okay. Now, how did we start when we saw that simulation that we never actually saw them do? We said, okay, well, the probability of this happening, where is it? Here, right? This is an area in the tail. We found that it was very small, right? And so then we said, well, that's actually evidence against H naught. Okay? So if we find that our p-value is small enough, that's big, right? then we have enough evidence to reject H naught. Okay. I'm going to need a fresh page here for step 4. Your conclusion. And I break the conclusion up into 3 parts. Okay. But if the p-value is small enough, and don't worry, we're going to have rules for that. Okay, what's small enough? But if the p-value is small enough, we have enough evidence to reject H naught in favor of HA. Okay, and I'm going to put the in favor of HA in brackets because what I want to emphasize here is that your conclusion has to be about H naught. You did all your testing assuming H naught is true. Now, do you have evidence for it or against it? Okay. So here, your conclusion must be about H naught since we did all our testing assuming H naught is true. If you find that you're going to reject H naught, then yeah, I would offer up in favor of what? In favor of the alternative. Right? And so now, yes, it's a little bit inappropriate, but it does help. Where is it? Of course. I know. What a way to lead you on. I said it's a little bit inappropriate. Hey. If the P is low, then the null hypothesis must go. Kind of rhymes. Usually on the final exam, I see it scribbled in the margin somewhere because it is helpful. So that's why, come on, paste. I'm scared to overwhelm it. Come on. Well, that's it. I need a new iPad. Could just restart it. Yikes. Or it does it for me. See how much we lost. Hey, not bad. Just doesn't want to do the image. Snoop. Where is he? Okay. I'll paste it in later, I guess. I don't know. But now it's all hung up. Hung up on Snoop. Now it won't let me do anything. Okay. Don't close the Zoom, Emily. Do not do it. Safari can close, Desmos can close. Oh my gosh. Well, this isn't a good sign, is it? Okay, I'm not going to try to paste it again, but I will paste it before I post them. Okay, because it is helpful. Okay, so, right, what's it saying? If the P is low, so if the P is small enough, okay, then we have enough evidence to reject H naught. Okay. Now, what's small enough? Less than the critical value critical level, sorry. Critical value Z star, they're all intertwined, so it's not a huge deal. But the critical level is called the alpha level. There we go. Alpha is the fish, right? And so the alpha level is the critical level. Okay. Now our default alpha level is alpha equal to 0.05. So if the p-value that you found in step 3 is less than 0.05, then you have enough evidence to reject H naught. Now, a lot of questions, I might say use an alpha level of 0.1, use an alpha level of 0.01. And it just depends on what field you're in, right? Just broad strokes, 0.05 is the default. I think finance is happy with that. Things like medical supplies, think about, you know, pills have to work, syringes have to be the same size always, that kind of stuff. So then they would lower this a little bit, right? They might use 0.01. Or if you want to be really open to being wrong 10% of the time, then you can use 0.1, right? Or if you have a really small data set and you still want to publish something, then you can bump it up to 0.1. But the default is going to be 0.05. So if it's less than 0.05, then you have enough evidence to reject H naught. Okay. Oh boy. Okay. Let's see here. I guess pretend you don't have this quite yet. We can use a confidence interval to test the hypothesis instead of doing the formal calculate a z-score, use the z distribution to find the area under the curve, which is the p-value, compare it as a less than 0.05. Wow, that's a lot. That's what we're going to be doing, right? But what we could do is we could say, okay, on the flip side, what if I make a 95% confidence interval? Okay. Then I'm 95% confident that my population parameter or proportion in this case is between these two values, right? Notice that 95% and the 0.05, the 5% left over between the tails, right? So they are related in that way, but I think that's a little bit too deep for today. We'll get there, okay? But just know that they're linked and they kind of go hand in hand, okay? But what we can do is, if you have a 95% confidence interval, right? And this one we have done. So we found a confidence interval for the proportion of American Facebook users who think Facebook categorizes their interests accurately as 64 to 67%. Kind of a lot of rounding happened there, but whatever. Based on this confidence interval, do the data support the hypothesis that I would say the majority of American Facebook users think Facebook categorizes their interests accurately? Now, one of the things I'll point out here is we're going to use this majority quite a bit. What does a majority mean? It means that the proportion is more than 0.5 or 0.50, let's 50%, right? In order to be a majority, has to be more than 50%. Okay? And so that's kind of a sneaky one. And I know it comes up on your assignments as well, where they just say, is there proof that is there evidence that there's a majority, blah, 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 blah. Okay. And so that's nudging you in this direction here. P greater than 0.5. That's going to be your alternative hypothesis, right? What's your jumping off point? Your jumping off point would have to be that P is 0.5. I have to assume that it's 0.5 until I can prove otherwise, and I can prove that it's potentially greater than 0.5. And 64 to 67, let's write that down here. So I have 64 to 67. If I put that on a number line, right, and maybe I'll space these out here. If I put these on a number line, 64 to 67, 50 is outside this interval, right? So now I'm 95% confident that these things are greater than 0.5, right? And so now, because this, my hypothesized proportion is not in the interval, that's evidence against H naught. So it's kind of like a quick and dirty hypothesis test. If you have a confidence interval, you can use that interval to, as long as you have the hypotheses set up, right? Then I'll put an arrow there. The null value, which is this null value here, 0.5, is not included in the interval, which means that we can reject the null hypothesis. Hey, she even says, this is a quick and dirty approach. It was incepted. Or we just agree on pretty much everything. She's so cool. Quick and dirty approach for hypothesis testing, but it doesn't tell us the likelihood of certain outcomes, right, under the null hypothesis. So it tells us that, yeah, no, there's evidence that it's greater than 0.5, right? But what's the probability of that? And so that's where the p-value comes in. Okay. We'll talk about decision errors today. Then we don't have to mention them next day. We have to know them, but it's just going to be one of those memorization things, or at least for a little bit. If I use an alpha level of 0.05, I'm saying that as long as the area in the tail is less than 5%, I'm going to reject the null hypothesis, right? There's still that p-value chance that I'm wrong, right? And what I'm saying is I'm okay with being wrong 5% of the time, right? And so that's what the alpha level is saying. I'm saying, hey, I'm okay to making this error, this decision error, 5% of the time. Okay? There's also the other way. What if I don't reject H naught, but it should have been rejected? Okay, and so the go-to example is if you're, you're in court, and so sometimes innocent people are convicted and guilty people walk free, and so we can have those decision errors happen, right? And so what we're going to have is there is some truth, right? There is some population, it exists, but we can't know what it is, right? And so that's one of the problems. And so the truth can either be that H naught is true, P is 0.5, or HA is true, P is greater than 0.5, right? We don't say what it is, we just say, well, it's greater than 0.5, do more testing. Our decision from our hypothesis test can be either to fail to reject H naught. Notice how it doesn't say accept H naught. You never accept anything because there's a p-value chance that you're wrong, right? And so you're always guarding yourself against saying something definitive. Well, I failed to reject H naught. Okay? And so if I fail to reject H naught, right, then and H naught is true. Well, that's fine. I'm good, right? If I fail to reject H naught, but HA is true, so if I say, well, there's no evidence to suggest that P is not different from 0.5, so then, but if it actually is greater than 0.5, for example, then I've made a type 2 error, it's called. Okay. A type 1 error is when I reject H naught when I shouldn't have rejected H naught. Okay. And the type 1 error is the one that we're mostly concerned about, right? When I reject H naught when I shouldn't have. Okay. And so let's see here. I feel like it's in here. Oh no, oh no. This is the alpha level. So the probability of a type 1 error is the alpha level. I like to memorize this table to keep track of which one is which. And what I'll do is I'll leave you with this for Wednesday because I'm all out of time. And we'll pick up there. If you have any questions, let me know. Otherwise, I'll see you then. Good.